Okay, so good morning. Let's start our lecture on of CEE, and today is about asymptotic observers. So what is the problem here? The problem is this. We have seen that in some cases, you want to do feedback by feeding back the state. But it is not always practiced to or feasible to measure directly the state. Why? Well, the state can be a mathematical entity. So in that case, you are not able to measure this quantity. Or in some other cases, it is absolutely impossible to measure the state. Imagine that you want to control the temperature in a glass oven. A glass oven, forno de vidro, it's the best approximation to hell that you can imagine. Forno de vidro é a melhor aproximação do inferno que podem imaginar. So imagine that you have a lake of molten stone, so very high temperature, close to 1600, so 1600 graus, and it bubbles, and you see fire. It's terrible. I mean, you wouldn't survive 5 seconds there. So in this case, you have you want to measure the temperature, of something which is at temperature of 1,600 degrees Celsius. And how do you do it? I mean, if it is at the surface, you can use a pyrometer, an optical pyrometer that uses the radiation. But if it is inside the molten glass, how can you do it? You can't place there a thermocouple because a thermocouple is made of materials that melt at 700 degrees, so less than half the temperature of the molten glass. So these two reasons, situations in which you can't measure the state because it is a mathematical entity or because it is technically impossible, are examples of motivations for using using the model of your system to estimate the state. So, what is the problem? Suppose that you have a system described by the linear state equations in continuous time. You can do exactly the same thing in discrete time. So you have x naught equal to ax plus bu, and you do measurements of y, the output is what you measure, equal to cx. Okay, so this output equation is a model of your sensors. We have discussed that. And we have our physical system that is, we assume it is described by this model. And we want to build a mathematical entity, if you want an algorithm, that looks at what you can measure, so y, and also the excitation of the system u, and estimates the state. So I put a hat on the state, okay? So the hat is not because X should wants to protect from the rain or from the excess of sun, but it is just to remind us that X hat is an estimate of the true state X, okay? And you call this an observer, in Portuguese, observador, or a state estimator, estimador de estado. Now, our class is devoted to this observer, state observer, and how can we couple it to the controller by, instead of feeding back the state, feeding back x hat, the estimate of the state. Now, this observer will probably be described by some mathematical model. Okay. Now, I have a question to you, and the question is, how can we build this observer? Okay. So before you go on thinking about this, and before you start giving me your suggestions, let's go to the whiteboard. Okay, so we have our system. We have our system, input U. This is described by x dot equals to ax plus bu, and you do measurements y equals to cx. Okay, this is our model, and I assume that I know a, b, and c. And now I want to build another system that uses the available information on y and u and generates some x hat, some estimate of the state. So this is a state estimator or state observer. Okay, so how can we do it? You have any suggestion? There is one thing that sometimes we are tempted to say. We have y equals to cx. So it's tempting to say something. If you want to have an estimate of x, what is tempted? What is a temptation to say?
Invert C and multiply by Y.
Okay. Why does it not work?
Because C might not be invertible. No, C is okay, yeah. C might not be invertible.
C might even be not square.
Exactly, yeah.
It can be not square. So C in many cases, suppose that you have just one output, C is a row, so it's not invertible. So it does not work because it does not exist. Good. Okay. So if you look inside through Y, well, does not work. In many cases. In some cases, it works. For instance, if the state is a position and a velocity, and if the velocity, if you observe the position, then you can differentiate the output to get the velocity. But that is not a very good choice, a very good option because of noise and so on. And this is for a specific case. Now, any other suggestions? Look at this. You can look through y into x. Now, where can we also look to the system?
Through the state estimator from the input.
From the input. So we have, and if I look at the input, what can I say? So this is something that I just cancel. So what is the idea?
we can replicate the system in the state estimator, for example.
So you write something which is a replica of the system now with a state estimate, which is something like this. Okay, so if you integrate this equation, our hope is that x hat is close to x because we have our system, which is more or less the same. A x plus b u. Now, is it true that since they share the same equations, x hat and x are the same?
No.
Why not?
Because of disturbances,
I
unknown
can have
disturbances.
disturbances. I can have disturbances. So disturbances act on the real system and do not act on here. Okay. Also, I have the problem of initial conditions. An initial condition can be created by a disturbance that, an impulsive disturbance that acts on the system and not, of course, on your software. So how can I analyze this? I define an error, which is x minus x set, and then I get an equation for x tilde. And maybe I can.
We
Yes,
could design the controller to take the error to 0.
I could not understand the beginning.
We could try to design something like a controller to follow the reference 0 between the x and the x.
Okay. Yes, that is something that we are going to do. This is a kind of open loop observer because let me clean things. So we have something which is the same u. And then we have the replica. And this gives me some x hat. X hat dot equals to a x hat plus bu. Okay, so this is a kind of open loop system, and there is no. Maybe we could do some correction. There is no connection between this x hat and x, and probably we could take advantage of the fact that we are measuring y, which is not taken care here. So actually, we are going to use a kind of controller, as you said. But before that, what happens to x tilde? What is the equation? How can we get an equation for x tilde? We can subtract these two equations. So we have x dot minus x tilde dot. This is what? X hat dot. This is what? That's the derivative of x tilde. And then we have ax minus ax hat. The multiplication of matrices is distributive, so this is a x tilde, and then bu cancels with bu. Okay. Now, what can I say? How can I proceed with my analysis about x tilde? X tilde satisfies this with some initial conditions. So x tilde of 0 is what? Is the initial error. So x of 0 minus x tilde, x hat, sorry, of 0. So x tilde of t is, you remember? If I have
exponential of a t minus t0.
Okay, let's suppose that to simplify that t0 is 0 times x tilde of 0. So conditions for the conditions for x tilde to go to 0. What are the conditions for x tilde to go to 0?
The eigenvalues of A must be negative.
So all the eigenvalues of A must have a real part which is smaller than 0. Now, is this a very much restrictive condition or not? What do you think? For in thinking that then you want to do some feedback of x hat. Is this very stringent? Is this a heavy condition that rules out very important cases? What are we ruling out here?
And non-stable systems.
Unstable systems, that's right. But unstable controlling unstable systems is a very important application of control. You want to stabilize an unstable system. So you could not apply this observer because the error would not go to 0. So you would not be able to use this estimate for feedback. Okay. So this rules out unstable systems. That's a very, very heavy. And even for stable systems, you see that the rate of convergence to 0 of x tilde is the same as the rate of convergence of rate of change of the states of the original system, because the matrix of dynamics is the same. The eigenvalues are the same. You see? The eigenvalues of the matrix that is the dynamic of the error is the same as the eigenvalues of the matrix which is rules the system, because it's the same matrix. This means that when x tilde go to 0, x has already gone to 0. You see? So you only have a good estimate when the important part has already elapsed. And it's not a good choice. You would like your convergence to the true state to be very fast. So let me give you an example, pictorial example. So suppose that this is time and you have your state. Okay, and your state is something like this. Okay, and what you would like to have is something that you start. So in blue, this is your true state. Now let me put here, say you have an initial estimate, let's say it's 0. And you would like that it approaches quite fast x, and then it tracks it. Okay, but what you have is something which is the error is very big. You see, it takes a long time. The time constants of the green system are the same as the time constants of the blue system. Instead, you want the observer to have much faster. You want to be in the red situation. Any question about this? Okay, so what happened was that someone, actually, he was not much older than you. I mean, all discoveries are made by young guys. Newton did his discoveries when he was, I think, 24, and Einstein also did most of his work when he was in the age of the 20s, mid 20s. So that means that you still have the hope of finding something really important. I won't for sure find anything important. Okay, so it was a guy called Leuenberger. Okay, David Leuenberger. He was 26 when he did the suggestions of adding here a term, which is plus again that multiplies the difference between y of t and c x hat of t. Okay, so he picks up x hat, multiplies by c, and he has a kind of y hat. So this is a kind of y hat. Okay, so it's what you expect y to be. Then you compare it. You compare it with the true observations of the output. By definition, you have it. Okay, so you put output error, and you multiply by some vector L, and you add it here. Okay, this corresponds to this extra term. Now, if you add this term, then how do we change it? It's, remember that y is cx, so put c in evidence. So you will have minus because of that minus, L, C, and then you have x minus x at, which is x tilde. So the equation now becomes x tilde dot equals to A minus LC x tilde. Remember the story of the controller. Let's write it here. You have x dot equals to A x plus BU, U equals to minus K x. So in closed loop, x dot equals to A minus BK x. And if A minus BK, if A minus BK controllable, then you can place the lambdas everywhere. Okay. So if the pair AB, better to say, if AB controllable, then you can place the lambdas everywhere. Now here, what we do, we build this structure. So this is the equation of the observer. This is the equation of the observer. Everything here. Okay. So x hat dot equals to ax hat plus bu plus L, and then the output error. Then the output error. Okay. And the error, the estimation error, verifies this equation. So can you state a similar theorem as this one for the case of observation? Now you want to adjust L. So what would you like it to happen with respect to L? How do you state your state estimation design problem? Is selecting L. How do you select L? You want your observer to converge your state estimation to converge to the true state fast, in a fast way. Okay, so what are you imposing when you say this rate of convergence?
All the eigenvalues negative and further from the origin.
Eigenvalues of what?
Of
which matrix?
Of the matrix A minus LC.
So you want to impose the eigenvalues of the matrix A minus LC, and you want to have them all in the left complex plane. Okay, and you are saying that they should be away from the origin. So if I could have this situation, this ping situation, this is even better. Okay, do you agree with me?
Yes.
Yes.
And this corresponds to what have I done with the eigenvalues to pass from the red to the pink situation?
They are now even further away from the origin.
Okay, more to the left, more to the left. So the pink ones are more to the left than the red ones. Okay. Now, actually, I disagree with you. I mean, I disagree in the fact that the pink is not necessarily better than the red one, but for the moment, let's assume it is. Now, let's, before discussing what I'm saying, state, is it possible to place the eigenvalues of A minus LC as in the left as you want? What do you suspect? What is your intuition about the condition on A and C? By comparison with the situation of the control.
Must be observable.
Must be observable. If the pair, so the result is if AC controllable, observable, then the lambdas of A minus LC can be placed anywhere by the choice of L. Okay, by the choice of L. So once you decide the eigenvalues of the error, okay, then you select L such that A minus LC has these eigenvalues. We are going to see an example how to do it in a moment, but before that, actually it is true. So you can do it when the pair AC is observable. Okay. Before that, let's discuss one thing, which is, do we really want the observer to be the faster the better, or is there a limit for that? In the case of the controller, you remember that there was a limit, and the limit was saturation. I mean, if you specify your closed loop system to be very fast, then your gains, your eigenvalues are much displaced, and your gains are very big, and your actuator saturate, and the theory is no longer applicable. Now, here you don't have saturation because this is pure software. You don't have any mechanical or electronic parts. It's just numbers in a computer because the observer is pure software. Okay, it's a sensor in the sense that it estimates x hat made of pure software. Okay, and of course the observations of the other sensors. Now, so we can have very high gains. L can have, I mean, 10 to 200. It's an incredible number. But maybe there is something else. Can you figure out what is the problem here that limits how fast you want your error to converge to zero? The problem is that we can have modeling errors. So remember that x not equal to ax plus bu is just a model. Then you have some error here, some delta, which is an error. Okay. And usually this delta is an high frequency function. That is to say, this delta corresponds to something that pops out only when in high frequency. You are, for instance, neglecting small masses. If you have a robot, okay, then you have very small masses, and you are neglecting these masses in the equations that describe the robot. And these masses move much faster than the rest of the robot. Okay, so if you do small movements, this mass is okay, will be well behaved. But if you start exciting the robot with high frequency movements, then these small masses can start to be excited, and they start moving, and they destabilize the whole system. Okay, so the modeling error can appear if you increase very much this L. This means that Y starts behavior in different way to predict. So this error does not go to zero because of these modeling errors, and the L very big amplifies this high frequency dynamics that would be otherwise very small. And if you then reinject your state estimate using a controller, then you will be into trouble because you can even get instability. You see? So there is a trade-off, and the trade-off is you want to make your state observer a bit faster than the system, but not too fast, okay? Because of the modeling errors. Any question before we move to the slides and consolidate these things?
Sorry, Professor. Could you repeat why it wasn't good to have an estimator as fast as the system?
Because of the noise of the modeling errors, this delta term that appears here. This delta term corresponds to things that are only think in terms of, let me clear up a few things to gain space. So I clean here.
I don't know if I explained myself right. I'm asking why the green solution isn't a good one.
Oh, why the green solution isn't a good one, not the fast one?
So yes,
okay,
so
because
it is. It has the same velocity as the system.
You would like, suppose that you would like to do feedback, and you can't do feedback of x, so you do feedback of x hat. So if your estimator behaves like this green solution, what is important in control is the transient. Okay, if the system is open loop unstable, you want to catch the transient to stabilize it. if you only, or suppose that your system oscillates very slowly and you want to make it fast. So you don't want to have a good estimate only when the transient has passed away.
Okay.
Okay. So this is, you would have a good estimate of the state in the green case when the important part of the dynamics has already passed. But this is what you want to control, to counteract it, to make it faster, or to make it, to reshape it in some way. Okay. But you haven't seen it because your estimator is so slow in catching the reality that it only catches the reality when it is too late. That's the reason, the intuitive reason. Let's say.
Okay. Thank you.
Okay. So, any other question? Okay. So let's go to the slides. Everything that I said, at least the mathematical part, is in the slide. So you have here the open loop observer, then the analysis to compute the error equation, and then the closed loop or asymptotic observer or state estimator, okay, and which is defined. This is the equation here that defines the state observer, and L is something that you have to design. And this is the error equation for the state observer. Now the dynamics of the error equation is A minus LC. So you shape L so that A minus LC has eigenvalues where you want. Okay. Now let's see one example. Suppose that we have this double integrator system. Okay. And let's do it. Let's do it. So first we have to write the state equations. In this case, it's just, well, you have here x1. So at the input of the integrator, you have x1 dot, which is x2. So x1 dot is x2. Then at the input of this other integrator, you have also x2 dot. X2 dot equals to u. And y is equal to x1. So you write it in matrix form. So this is something that we have done several times. Now we build the matrix A minus LC. Okay, just multiplying and adding matrices. Remember that L is a vector, is a column vector. C is a row vector, so you have here a matrix. Okay, and if you add these two matrices, you have this stuff. Now, compute the characteristic polynomial for the error, which is the characteristic polynomial of this matrix. Determinant of Si minus the matrix, which is A minus LC. So determinant of Si minus A plus LC. So pick up this and S minus L1 minus 1 minus L2 S minus 0, which is S. And you compute the determinant and you get this. So this characteristic function is the characteristic polynomial of the error of the that corresponds to the matrix that defines the error, A minus LC. Now, suppose that you want to have the the eigenvalues of the error dynamics in both in -1. So your desired characteristical polynomial is S plus 1 squared, which is S squared plus 2S plus 1. Okay, you could have decided otherwise. In that case, the example would be different, but the procedure is the same. Now you compare this polynomial with that polynomial, and you come to the conclusion that L1 is 2 and L2 is 1. Okay, and you have designed your controller. So go to the equations of your observer, and now you have TL. So the I'm sorry, the observer is a dynamic system. Okay, it's a dynamic system because it replicates the dynamics of the system, of the physical system. And now you have this design, this L vector. Any question about the example? Of course, you can have, okay, about the about the effect of selecting eigenvalues in different positions. I have here 4 on the right, 4. So the observer poles are the triangles, and the process poles are the squares. And you should have the observer poles faster, that is to say, to the left, than the process pole. So situation A is usually the indicated one. So you have something in which you have an initial transient. Look now, this is the time response. The dotted line is the estimate starting at 0. And the solid line is the state starting at 1. So you have an initial transient. The arrow is the difference between the two curves, and one converges to the other. So state estimated, the dotted line converges to the solid line. Now, if you make your observer slower, that's situation B, so you approach the pole of, actually, these are two poles. This is two poles in the same position. If you approach them from the open loop system, then your error will take longer to disappear. And then you can start doing funny examples. For instance, in this case, we have the observer poles with the same real part, but with imaginary parts. So you have an oscillatory behavior. Usually, this is not a good choice. Okay? Usually, you don't want to have an error which is positive and then negative and then positive. Okay, this was done just for illustration purposes. Or you can have the observer poles slower than the poles of the system. In that case, you have something which takes a long time to converge. You see, it's slowly converging to the solid line, and it reaches the solid line only when the transit has died out. Okay. Any question about this example? So definitely we want to be in situation A. Okay. How far away, how far to the left should you place the poles? There is a rule of thumb, which is 4 to 10 times the value of the real part of the plant poles. Okay. But this is just a rule of thumb. Okay. Okay. So remember these practical issues, and so the eigenvalues of the aerodynamics, they should not be too small to avoid the error going to 0 slowly. So you want your observer to be fast, but not too fast, because of the error in the model, of the modeling errors. You can design the L polynomial using the method of unknown multipliers, as we have done it. So that method of equating the coefficients, or you can have systematic systematic methods, and you can derive, for instance, a Bhaskara type formula. I have this in the form of an example that you can try to. This is not it's not impossible, but it's a problem which I consider not to be a simple problem, but it is an interesting problem. And that you, when you study these slides, you can do is to try to get an observer or a Bhaskara type formula to design AL using the same type of arguments as that we used to design the Bhaskara formula for the control. Okay, so here, these two slides are a help for that. Now, if you go to MATLAB, you won't find any. If you want to find any say Ackermann formula for observers or place function for observers, and this is because you can use the same functions by replacing the matrix A with A transposed and the matrix B with C transposed. Okay, so if you design a control problem with A transposed and C transposed, then what you really are designing is a vector L of gains. Be careful, because the result is in terms of a row vector and L is a column vector. So, but apart from that, the numerical values will be correct. Okay, so you really don't need new functions for the observer. Any question? Okay, now let's put everything together. So we learned how to design a controller by state feedback, and we learned how to design a state estimator without state feedback. Okay, now let's put everything together. And to put everything together, what do? We have our system, x dot equal to ax plus bu, y equals to cx. So I know A, B, and C. And my controller is made of an observer according to this equation. This equation is a replica of the system equation plus a term related to the output error. And here, this is rewritten in a slightly different way, but it's completely equivalent to this. And then I do the estimate, I do the feedback, not of the state, but of the estimate of the state. Okay? So you have your system, which is this dotted line block in the top, and you have your controller or compensator system made of the observer plus the feedback of the estimate, state estimate, which is also a dynamic system. So globally, remember that you have two n poles, okay? Because you have n poles from, or n eigenvalues from the system and n eigenvalues from the observer, okay? So the order of your system is 2n. Now, you have, in order to design K, the vector of feedback gains, and L, the vector of observer gains, you have to, you know how to do it. So you design K by looking at the eigenvalues of A minus BK, and you design L by looking at the eigenvalues of A minus LC. Now, when you put everything together, where are the eigenvalues of the whole system? The answer is very simple, and I'm going to show it. it's the eigenvalues of A minus BK and the eigenvalues of A minus LC. That's why we call it a separation theorem, because you can design the controller in a way that assumes that you have no state estimation, and the state estimator assuming that you have no controller, and both things together, they give the eigenvalues of the closed loop system. Okay. So before proving that, we need this lemma on determinant. So suppose that you have a matrix made of submatrices. So you have a matrix made of matrices A, B, C, and a block of zeros. And you want to compute the determinant of this structure. Okay. And we can prove that this determinant is the determinant of A times the determinant of C. So it's more or less as they were scalars, but you can apply this rule for matrices made of blocks. Of course, A and C must be square matrices, even of different dimensions. Now, to prove this, first consider the matrix which is made of a diagonal of blocks. Okay, so I is the identity matrix, and then you have the C matrix, and 0 and 0 are blocks of matrices. Okay, now start developing this determinant from the top left element. So it's 1, and it's the determinant of the matrices that you get by deleting the first row and the first column, plus 0 times the corresponding determinant, 0, 0, 0. So it's just 1 times a determinant of a submatrix. So this is 1, 1, 1, 1, 1, 1 times the determinant of C. So this is just the determinant of C. If you do the same for this other matrix made of A, B, 0, and I, and you start developing the determinant now from the lower column than the last column, you go on progressing and you get 1, 1, 1, 1, 1, and then the determinant of A. Now, observe that you can multiply matrices defined by blocks using the usual multiplication procedure, provided that the dimensions are compatible. And you know that this matrix ABC upper triangular by blocks is the product of these two matrices, because this is IA plus 0B, so that's A. Then I and B is IB plus 0I, that's B, and so on. Now, the determinant of a matrix, or the determinant of a product of matrices, is the product of their determinants. So the determinant of ABC0 is the determinant of this first matrix times the determinant of this other matrix. But this determinant is C, and this determinant is A. Okay? So the determinant of ABC0 is just the determinant of A times the determinant of C. Now let's use this result. Remember, what we have proved is if we have a matrix made of blocks that is upper triangular, the determinant is just multiplying the determinants of the matrices in the block diagonals. Okay. Now let's go back to our original problem, and I have my system x dot equal to ax plus bu, y equals to cx. Then I have x hat, and I have that u t is minus k x hat. So let's start by eliminating this u variable so that we have a kind of autonomous system. So I replace u by minus k hex hat on the first equation and on the second equation. Okay, and I group things together and I get this stuff. where U now has disappeared because I'm using this control law. Now, I could write this thinking of a big state X and X hat, but I prefer to do another thing, which is to define X tilde equal to X minus X hat, and to replace the last equation by the equation for X tilde. Okay? Now, it is possible to prove that the eigenvalues of this set of equation with X and X hat is the same of the eigenvalues of this other set of equations. Why? How can we do it? Remember, we have proved that if you do a linear change of coordinates, so if you have your state and you multiply the state by matrix, you get another set of state variables, but the eigenvalues remain unchanged. And when you do this change of coordinates, actually, you can show that this corresponds to multiplying the amplified state X and X hat by matrix to get this other state X and X tilde. Okay, so X and X tilde are obtained from X and X hat by multiplying by a matrix, which is made of ones and zeros, and you can show the determinant is 1. Actually, this could be an exercise. So let's look at the eigenvalues of this matrix. So I write these two equations in matrix form. So my state is now made of X and X tilde. And my matrix is a big matrix, okay? Made from these two other equations. Now, compute the characteristic polynomial of this big matrix. Okay, this is just Si minus this matrix, and you can write it in this way. So here in BK you have minus BK. On this upper block is Si minus A minus BK, where I is dimension n, the identity of dimension n, and the same here, A minus LC, Si minus A plus LC. Now we can apply the lemma for the computation of the determinants, because we have a block upper triangular matrix. So the determinant of this big matrix is just the determinant of the upper left block times the determinant of the lower right block. So these things that are here. But this is nothing more than the characteristic polynomial of the so-called controller part, that is to say, of the system controlled, assuming that we have no observer, no state estimators, and this is just also the characteristic equation of the observer part. Okay, so when you do this, remember, we assume that our control is minus kx hat, not kx, but we still end with the same eigenvalues for the whole system. So the eigenvalues, assuming that you have an estimate of x, although you have it of x tilde, and the eigenvalues of the eigenvalues of your observer. So this concludes the proof. Questions? So the next thing will be to give an example, but I will stop here, and in the next class we will look again at this theorem of the separation theorem and provide a whole design example in which we design the controller, the observer, we put everything together, and we see this stuff in action. Any final question or comment or? Okay, so have a nice weekend.
Okay,
too,
thank you.
Professor.
Have a nice
Thank you.
weekend.
Have a nice week.
Have a nice weekend, Professor.
Thank you.